Alright folks, I want to go over the exam today. It's probably my shortest class, and then I'll answer any questions that you have about previous visits. The exam is, I think it's next Tuesday at 8 a.m. Okay, next Tuesday at 8 a.m. It'll be a midterm. It'll be 30 questions. It's worth, what, 200 points, is that right? And it'll be very similar to previous exams. Half of it will come from the previous two chapters, so that's chapters 10 and 14, I think. That's the chapter on electricity, static electricity, and then also the chapter on, geometric light. And then the other half of the exam, the other 15 questions, will come from previous quizzes. They'll be very similar to previous quizzes. I'm going to go through and I'll pick out 15 questions from those quizzes, and then I'll change them. So I get a numerical problem, I might change what value I'm looking for. Of course, I'll change the numbers. If it's like a conceptual question, the question will still be about the same concept, and even about sort of framing around the same idea, but I might ask a slightly different thing. As we go over this, I'll give you some later. But, yeah, it'll go on. And you'll have the same equations but I'll add factors 10 and 14 and I'll put it in order, meaning the old stuff first, in order that we got it, and then the last part. Okay. I can put the answers in order too, so that A is the correct answer, and then they increase and level for each grade. C, okay. Okay, got any questions about the format of the exam? Okay. I haven't actually projects ready, but I'll try to get them this week. Like, definitely for the exam. Yeah, that's it. Alright. Let's first go over just sort of reviewing chapter 10 and 14. I'm just going to sort of give you a summary of what all we did in those chapters. You should have this already in your notes. Talked about the two different types of charge. We have positive and negative charge. Positive and negative charge. We talked about how charge is conserved. Again, this should be in your notes. Charge is conserved, and then like charges repel, opposite charges attract. Repel, attract. Talked about Coulomb's law. Coulomb's law describes the force between two charges. That's K/Q over R squared. And the unit of charge is the Coulomb. Talking about how charge is quantized, that means that it comes in particular units of the fundamental unit of charge, and the fundamental unit of charge, 1e, is equal to 1.6 times 10 to the minus 19. That would be on your equation 2, of course. And so the charge of an electron is the negative of this value. The charge of a proton is the positive of that value. Let's see. Talked about an electric field. Electric field is just a force per unit charge. I don't think we said this, I don't think I put it in equation form like this, but it's just a force per unit charge. So it's charge within an electric field feels a certain force. And so the field is just a way of describing that force that a charge feels. It's really a sort of a theoretical construct that we make up, but it describes the force that a charged particle feels, and that charge is being described by Coulomb's law. We also talk about voltage, our potential difference. Voltage is energy per unit charge. So if electric field is force per unit charge, voltage is similar, it's energy per unit charge. So this is how we describe batteries. Like for example, a 9-volt battery means that it provides 9 joules per coulomb of charge. And then we talked a lot about sort of the electric potential energy and how the potential energy of a charge changes based on its voltage. So a battery, for example, with more voltage will give an electron more potential energy, which will be used to do whatever your circuit is that it wants to do. Let's see, also current. We talked about current. It's just the flow of charge. If I have a wire, I have charges flowing through it. The current tells me how much charge in a given amount of time passes. So it's Q over T. It would say, for example, at this point, how many coulombs of charge pass in a given amount of time? How many coulombs per second? The unit for this is the amp, and it's 1 coulomb per second, the basic SI units. But the units for current are the amp. So we worked through some examples. Talked about conductors and insulators. And the properties that differentiate between these two. Conductors have lots of free electrons, and those electrons can move around freely. Insulators don't have a lot of free electrons. So in conductors, those free electrons can carry electrical energy from one point to another very easily. And for the same reason that electrical conductors are also good thermal conductors. So for example, copper, which is a really great electrical conductor, is also a good thermal conductor, because those free electrons can transfer energy. Let's see, and then moving on to magnetism. So this is just meant as a review, a quick review. We worked through some example problems of these as well. Talked about how permanent magnets are formed, and then also about the concept of magnetic domains. The magnetic domain just describes an area within a material, and if the magnetic field of all those electrons that are in that material, if they're all lined up in the same direction, like in this case, for example, if these are my magnetic domains, if the magnetic domains are all lined up in the same direction, then that is a permanent magnet, and that generates a magnetic field. But every moving charge has a magnetic field. So like my body, for example, even though I'm not magnetized, or you as well, that all the little moving electrons, they all generate a magnetic field. So that's that concept of magnetic domains. And then there were a number of medical uses that we talked about, how you can direct a catheter through the body, you can remove bits of iron from the eye, you can detect iron in the body, like with asbestos as well. Your nerves and your muscles all use electric currents, and those currents can be measured because they generate a magnetic field. So that was the MCG, that's the magnetocardiogram, where you do this magnetic imaging of the heart. And then the magnetoencephalogram, the MPG, and where you do magnetic imaging of the brain, because your brain and your heart generate a magnetic field, and that magnetic field can be detected. All right, that was chapter 8 to 10, right? And that was chapter 10. You should take a look at the homework. That'll be a good preparation for you for the test, and then just looking back over it as well. Any questions about chapter 10 or the real fast? Let's go on to chapter 14, that we did most recently. That was on light and optics. Chapter 14 was on reflection and refraction. Reflection describes how light reacts when it comes to a reflective surface, when it bounces off of a surface. That's here. Chapter 14, reflection and refraction. Reflection just describes how light, when it bounces off of a surface, it describes these two angles, and those two angles are equal. Theta incident is equal to theta reflected. And then refraction, we can think of it two different ways. Really, refraction is talking about how the speed of light changes. So if light goes from one medium to another, say it's going from air to glass, then it's going to slow down when it gets to the glass. So if I call this speed c, if I call this v, v is going to be less than c, because the light actually slows down when it enters into a medium. And we use the index of refraction to describe this. The speed is going to be the speed of light in air in a vacuum divided by the index of refraction. The index of refraction always has to be greater than what value? Or greater than or equal to what? What is the index of refraction for a vacuum? It's going to flow that it travels at the speed of light. Yeah. So the index of refraction in for a vacuum has to be 1. Right? So the index of refraction is always greater than or equal to 1. And then also refraction refers to this bending of light. So if I have light going from air to glass, it's going to bend one way or the other. And we talked about this whole marching band analogy, or using these wave fronts. If I imagine these wave fronts, this front waves as the light ray travels along, when it comes to the glass, this side is going to slow down, and that's going to cause this side to swing around. And so my light ray then will bend towards the normal like that. That's called refraction. And we looked at a number of different examples of this, like the straw in the cup, or I don't remember, in a lens, light in a lens. Okay? So you should be prepared to know which direction the light ray bends by looking at the medium going from one to another. If it's moving from a low index to a high index, that means it's going to bend towards the normal, just like in this case. But if it's moving from a high index, like from glass to air, that means it's going to bend away from the normal, like this. I always remember that. I was always going to this whole wave concept. And I thought, well, what does it do at this point? Does it slow down or speed up? If it slows down, it's going to move like that. If it speeds up at this point, it's going to bend the other way. We did several examples like that in class. After that, we talked about lenses. There were two different types of lenses, convex and concave. You need to know what they are and how they respond. Convex lenses and concave. Convex look like this, concave look like this. We talked about their focal length and what the focal lengths are a measure of. Remember, the focal length is measured two ways. It's the half of the center of curvature, but it's also the point where parallel rays focus. So for example, with the convex lens, if I have rays that come in parallel, like this, they're going to focus at a particular point, and that is the focal point. In a similar way, for the concave lens, I have rays that diverge, because it's a diverging lens, but it diverges in such a way that if you trace them back, they go through the focal point, like that. You also need to know strength, how to find the strength of these lenses. We measure this in diopters. It's the inverse of focal length, where the focal length, this is important, I said this in your notes, just to be clear on this, the focal length is measured in meters when you find the strength in diopters. You have to, usually when we're dealing with lenses, we don't have to revert back to the SI system, because usually the units all cancel out in the unit. But when you're dealing with strength, you do have to convert it into SI units. Right? That's really the only case when you're dealing with lenses. Alright, so that's the strength. Yeah. Are there items that are diopters? What do you mean?
I have a question. Whenever I say like, oh, find the length of the length of the focal point, and just you got to give us one of those numbers, right? And so you just say the diopter.
It would be pretty simple. I would just give you one number or the other. So I would say the focal length of this lens is 2 meters plus the strength in diopters. And that would be 1/2. or the strength of this lens is 1/2 by optics, so what's the focal length? And that would be 2. But it's going to be pretty straightforward. That's really the source of convex. Okay. Alright, good. Alright, so we use the strength. The strength is a measure of how much the light rays are bent or how much they're effective. Let's see. You also need to know about the different images that are formed. Also, in the course of this, you need to look back, but you need to understand that the convex lenses are converging. That means the light rays come together. The concave lenses are diverging. The type of images that are formed are real or virtual images. Real or virtual. Real can be projected onto a screen, like the image right here, or virtual images cannot be projected on a screen. Virtual images have a negative image distance. Real images have a positive image distance. I gave you a table. I think that'd be very useful for you to sort of memorize, I guess, or look over and sort of internalize about the different signs for image distance. And one of those was that a negative eye is virtual and a positive eye is real. I'll recap that here in just a second. You also need to know how to trace rays. I'll show you how to trace these rays. It's in your book as well. Let's say I have a convex lens. I have an object over here. I can trace rays like this, parallel to the axis, through the focal point, parallel to the axis, and then straight through the center of the lens, like that. And that tells me that my image is over here. It's going to be an inverted and real image. So this is in your notes. It's in the book as well. You can do this with a diverging lens as well. I think we just did two rays for this. If my object is here, I go parallel to the axis, and then it diverges, but it diverges in such a way that if you trace it back, it goes through the focal point. And that's how we describe the divergent lens. That's how we describe the focal length for the diverging lens. And then the second ray just goes straight through the center of the lens, and so that tells us that our image is right here. There's our object, image. All right. We also use the lens equation. You'll have to use this once or twice at least. 1 over the focal length is 1 over I plus 1 over O. So you need to make sure, there's some homework questions, you need to make sure that you can use this equation and manipulate it properly. Also, the magnification is negative image distance over object distance, but the magnification is also the image height over the object height. So if my image is twice the size of my object, that's a magnification of 2. If my image is half the size of my object, that's a magnification of 1/2. All right, I'm going to recap. You should have this table, but let me just rewrite it because it's pretty important. For converging lenses, I have a positive focal length. For diverging, I have a negative focal length. For virtual images, I have a negative image distance. For real images, I have a positive image distance. If inverted images, upside down images, have magnification less than 0, a negative magnification, and upright images have magnification greater than 0. Smaller images have the absolute value of their magnitude is less than 1. So somewhere between -1 and +1. It's a decimal number. And then bigger images, the absolute value of their magnification is greater than 1. All right, I worked through several examples with the length equation. Again, at least once or twice, you don't have to deal with the length equation. So make sure you're out on that. If you have trouble with the math of that using the fractions, please come see me. We can work through it. with 5 minutes, you'll be all proficient at it. All right, then we looked at mirrors. Which I guess we just did, we did mirrors, the concave, convex, and flat mirrors. So flat, you'll need to know what type of images they produce. Flat always produce virtual images. Flat mirror looks like this. If this is my object, my image is over here. That is to say that the image distance, or the object distance, is equal to the negative of the image distance. That tells me that my image distance is negative, it's a virtual image. My magnification is equal to 1. We talked about the field of view. For a flat mirror, I'm not sure if we call it the field of view, but the field of view of a flat mirror doesn't change, regardless of your object distance. That means if you take that mirror and you move it back and forth, you're still going to see the same amount. You still have the same field of view. So, then also concave and convex. Concave mirrors, convex mirrors. Concave mirrors look like this. They're caving in. Focal point is here. These are converging mirrors. So they have a positive focal length. Convex mirrors look like this. There's a focal point. These are divergent mirrors. Diverging meaning that if light rays come in, they go out. Converging, they converge like that. Alright? A concave mirror can both produce real and virtual images. It can produce upright and inverted images. We pass around a concave mirror, and if you hold it up real close, it looks so big, right? It looks like a makeup mirror. And if you hold it back further on, you can do it upside down. Right, so concave can produce both real and virtual, upright and inverted. However, convex mirrors only produce virtual, and only produce upright images, and only produce smaller images. A convex mirror is like a security mirror. Always remember that. You know, a security mirror, you always look small, and you always look upright, and it's always virtual. And concave is like a makeup mirror. Makeup mirror, if you hold it real close to the big and upright, you hold it that far away, and look upside down. All right. Let's see, so I think there's just one other thing on the human eye. And so the human eye is basically just a convex lens. Human eye looks like this. I have light rays that come in. They focus at the focal point of the eye. But then we also talked about how this eye has these little muscles along the lens, and they can make that lens fat in the middle, or they can make it real long and skinny, and that changes the focal point of the lens. So for example, if you're looking at something that's up close, it makes your focal length shorter. So that's what happens when your eye focuses. And you can see here that the light rays will form an image at the retina, but the focal point now, instead of being back at the back of the eye, has come in short, so it goes a shorter focal point. You might know that in class. The light at the lens in the eye comes inverted image, through the whole where it shows a picture of something. Because the little method is producing inverted image, and the brain switches to that, so you don't walk around and something. Nearsighted and farsighted. So you draw an image about nearsighted and farsighted, and the corrections that you can make. Pull that up. So there's the nearsightedness right here where your eyeball is too long. And this is your farsightedness where the eyeball is too short, and so the light rays focus behind the retina instead of at the retina. And then there are corrections for those. we can use convex or concave lenses to correct that. So there's a nearsighted eye on the top, and they use a diverging lens or a concave lens. It basically sort of spreads those rays apart so that when they come back together in the eye, they focus at the retina. And then in a similar way, instead of spreading the rays apart for the far side of the eye, they squeeze the rays together a little bit before they get to the eye. And that way when they're focused by the lens, they will focus at the retina. I'm going to put these on a little clearer on the website, these images. So you should know what near and far side is and how to correct it. Well, you may not write it down myself. Give me just a moment, okay? All right. So that's all of chapters 10 and 14, and the homework has been up. We already need to be working on that homework and make sure that you follow and understand that. You know, I will pull from the homework for the exam to make sure that you're up on that. The other part of the exam is the old quiz. So how do y'all feel about your quiz? Do you want to take some time on the quiz? No? Yeah. Let me see. Quiz 2. Anybody else have that problem as well for quiz 2? It seems to work okay. But just check your computer. Try it on your computer. If you still have trouble with it, just let me know. I can send you a file or whatever. Alright? Okay. Okay, let me show you. If you could see something like that on the test. That was the logarithm problem. I think that's problem number 5. Oh, the back. Oh, yeah. Let me show you. I forget what the answer was. What was it? Yeah, it was B. Yep, right. So the velocity is distance over time, right? And the velocity is 300 meters per second. The distance is what you want to know. And then the time. Now it takes 0.1 seconds to travel and then come back to the bat. So we really want to do 0.05 seconds here, half that time. Because that time is the complete flight time. And so then we find that D is 15 meters. Right. If you got 30 meters is okay. So it wasn't an option. Like 30, if you use 0.1, you really got 30 meters. Like I said, 30 meters. Let's look at that logarithm problem over here. Because you might see that on the test. Even though I took it off of this, I'm going to still hold you responsible for it. The way this should have read is what is the log of 10,000? Right, and so this is the same as the log of 10 to the 4th, and that of course is just going to equal the exponent. So the answer should have been 4D. And a number of you put that down, but I paid everybody that credit. So if you got it wrong, I paid that. If you got it right, the question is wrong. On the bottom, the equations of this, it's not on this question, on this one. It says that log of 10 to the x is equal to x. And so here, this 4 is my x. That's my 10 to the x. Oh, yeah. Okay. Right, yes, you're right. You're right. That's not what I meant. What's the log of 10 to the x? Okay, you're right. It should be 10,000, but that's not what I meant. You're right. Yes. Right. No, you're making sense. I'm not making sense. But let me say, let's just rewind. Of a more reasonable number. Let me give you an example. So I might say, what is the log of 1,000? And that's equal to 3. Or I might say, if the log of 10 to the x equals 4, what is x? And x would equal 4. Yes, so that part was okay, actually. But it's not what I intended. So. All right? That's good. Okay. You mean like, yeah, that's totally fair. That's totally somebody cool. Oil as well? What about? Yeah, so let's look at some of those. I'll give you all a flavor for how I'll change. I think that's what you're asking, right? Is how I'll change the question? So, if the topic is not covered on this quiz, on any of these quizzes, then it will not be on the final. But most topics are covered on them. So, like let's look at quiz 2, for example. Like for example, here, question number 3 about the basal metabolic rate. I could give you that, but I would give you different options for it. But basal metabolic rate obviously would be the same, would be similar. Here for question number 4, you throw a ball with a mass 2 kilograms up at a speed of 10 meters per second. How high does it go? The way that you did this is that you said that the kinetic energy was equal to the potential energy. All right, so I could change it in the sense that instead of saying that it goes, if you throw it up at a speed of 10 meters per second, I say that it goes up to 10 meters high, and then I want to know what is the speed that you threw it with. So instead of asking how high does it go, I can instead ask what is the velocity. You still work in the exact same way, where you set the potential equal to the kinetic energy, but you're looking for a different thing. Is that clear what I mean? In those problems, like how I'll change it? I can change the numbers in the problems as well as the variable that I'm asking for. But the approach that you take will be the same, whether you're getting energy or math or whatever. Let's look at some of these others. Here, you throw a ball up in the air. I could change sort of what these say about the kinetic and potential energies, the various options. But the idea would be the same, that as you throw it up in the air, the potential increases and kinetic decreases. Is that clear? Study the origin. Let's look at the study. Don't know the answers to the origin, but understand how we're all able to build elements. And understand the topic of study questions. And the answer to what? Oh yeah, there are many information. All right, if you have trouble with that, just let documenting it or just talking about it? Alright, so if there's no questions, then I will see you up on the next day. Okay? I'm not gonna have a help session. Huh? Whatever. Oh, I'll be here at the right time. Alright? I got some of a few things because I can't wait to do your test, or at least one of your tests. So just give me another 2 minutes, let me call out these names right here. And y'all can go.